Hello everybody, this video is going to be the first video for our equilibrium chapter. This video is going to cover Le Chatelier's principle. So the big difference between this chapter and other chapters is that we're really going to focus on reactions that can go both directions for this chapter. Normally we only think about reactions going from reactants to products. But in actuality, there are some reactions that can go backwards. We call them reversible. So for example, we could take this reaction and flip it. It could go forwards or backwards. Nobody wants to have to write out these, both directions every time. So instead of rewriting the reaction flipped, we just write it the normal way, and we replace this single arrow with what we call a double-headed arrow. That way you don't have to write it going both directions. You can just use the double-headed arrow, and that tells people that this reaction can go forwards or backwards. So there is a reaction rate going forwards. There's a speed at which you're making the chemicals on the right. There's also a rate going backwards. A reaction will reach a point at which the forward and the backward reaction are happening at the same speed. Every time you go to the right, you're also going to the left. You're making products, and then you're taking those products and breaking them down back into the reactants. You're going forwards and backwards and forwards and backwards. And if that happens at the same speed, to us, it will look like nothing's happening. If every single time, one set of compounds gets made, they also get broken apart, to us observing, it looks like the reaction has stopped. We say it has reached what we call a dynamic equilibrium. And that's trying to express the concept that even though it looks like nothing's happening, the reactions are still dynamic. There's still changes happening. It's just that they're happening at exactly the same rate. Forward and reverse are at exactly the same speed. That does not mean that the concentrations of the things are the same. Okay? You can have a reactant-favored reaction. You can have a product-favored reaction, where you have more product, right? If it's product-favored, you have more products once you reach this equilibrium point. So the concentrations do not have to be the same, just the speed at which things are being made and used up is the same. Sometimes they might be equal concentrations, but that's just a coincidence. It's not on purpose, okay? The concentrations do not have to be the same. So sometimes we want to find what we call this equilibrium point. And when we say the equilibrium point, what we're referring to is what are the ratios of products to reactants once you get to the point where the forward and the reverse reaction are the same. So once we reach this special equilibrium situation, we find out how much product do we have, and we compare it to how much reactant. Now, if you think about it mathematically, you could have different ratios that result in the same forward and backwards rates, right? There isn't just one equilibrium point. If you do something to a reaction to push it away from this equilibrium point, what will happen is that things are going to change. The reaction is going to proceed in such a way so that it can readjust its concentrations to find a new ratio where the forward and backwards rate are equal. Okay, so we say we will stress a reaction. We may do something like dump extra chemicals in there, or maybe we heat it up, right? Maybe we increase the pressure. We're going to do something that's going to push the chemicals away from their equilibrium point, and it's going to have to adjust. Maybe it starts making more product. Maybe it starts making more reactants. It's going to do whatever it needs to find a new ratio that allows the forward and backwards reaction to be the same. We call this concept of a reaction getting messed up and trying to fix itself and find a new equilibrium. We call that Le Chatelier's principle. So we say if a stress is applied to a reaction at equilibrium, the reaction changes to relieve that stress. It will find a new equilibrium point where the forward and backward reactions are equal again. It's going to try to undo whatever change you had made. So to really simplify this, if you took away a chemical or you took away some energy from the reaction is going to proceed in whichever direction will replace it. If I took away some of chemical A, the reaction is going to try to make more of that chemical A. If I add extra of something, maybe I add an extra amount of chemical B, or I add some extra heat, the reaction is going to proceed in whichever direction, forward or backwards, will use up some of that extra. Okay? You can therefore predict which direction the reaction is going to proceed. Is it going to try to make more of the chemicals on the right of the arrow, or is it going to try to make more of the chemicals on the left of the arrow? So how do we stress out a reaction? What can we do to a reaction that is going to take it away from that equilibrium point? You could change the concentrations. You could change the temperature. If it's a gas, you could change the pressure or the volume, because that's kind of the same as changing your concentration, isn't it? So it will have a similar effect. You could increase any of these, or you can decrease any of these. Here are some strange things about equilibrium. These are little tidbits that you have to know to be able to get some of the more complicated questions correct. So equilibrium is only going to be affected if you change an aqueous or a gas phase chemical. Okay? If you change a solid or a liquid, nothing will happen. That is a really weird concept. If you add more of a solid, yes, you can make more quantity of product, but your ratios of things are not going to change, and the point at which the forward and backwards reaction take place is not going to change. You have to be very careful that you don't mix up the question about the quantity of substance that can be made and the rate at which these things are being made and the ratios of these chemicals to each other. So the reason solids and liquids don't affect equilibrium is a really weird fact that they don't really have concentrations. Mathematically, when you start deriving the equations that we use, they don't have what we consider to be concentrations. So it's not going to change the equilibrium point. When we start doing some of the math, you'll see what I mean, where there's no place for those chemicals to be in our equation. Another strange thing is that while adding gases that are part of the reaction will change the equilibrium because they're participating in the reaction, if you add a gas that is not participating in the reaction, nothing's going to change. Yes, the pressure of the container will change when you add this new gas, but it's not going to change the ratio of chemicals that are inside the chemical reaction that's taking place. So if you ever add a noble gas, it's an inert gas, it doesn't participate, it's not part of the chemical equation. Even though the overall pressure will increase, the partial pressures of the gases that are participating don't change. So that effectively means their concentrations are not going to change. And if that's not changing, we're not going to need to find a new equilibrium ratio. Another thing that's tough for people to remember is that a catalyst is not going to do anything to the equilibrium point. The catalyst is only related to the speed of the reaction to get to your equilibrium point. It won't change the ratios of chemicals you have once the forward and backward reaction are happening at the same speed. So you'll get to equilibrium faster, but it's not going to change your ratios at that equilibrium point. So here's a quick example. You'll see in this chapter that we will add the energy to either side of the reaction. If it's on the left, remember it's absorbing, it's endothermic. If it's on the right, it's exothermic. So we'll just add that in sometimes. All right, so if I add more nitrogen, that's going to disrupt the ratios of all these chemicals, right? It now has way too much nitrogen present. So the reaction is going to proceed in whichever direction will use up some of this nitrogen. So it's going to proceed to the right. We say it shifts to the right. It will make more of my ammonia. Okay, I'm going to be making more of this in order to use up some of that nitrogen. So we say it shifts to the right to use up the extra by making more products. Now, what if instead of adding something, I took something away? What if I just remove some of the hydrogen? Well, now the ratio is disrupted, right? Now I don't have enough hydrogen present to have a good ratio of things. And so the reaction is going to proceed in whichever direction will make more of that hydrogen. It's trying to replace what I took away. So it's going to take some of these ammonias and it's going to break them apart and proceed in the backwards direction to make some of these reactants again. It's going to replace some of that hydrogen I took away. It's going to do that until it reaches a point where the ratios of all the chemicals are now at a good ratio again, and the forward and backwards reaction are back to being at the same rate. When I took this away, the backwards reaction started to become dominant, right? It's going to go backwards more than it's going forwards because it's trying to make more hydrogen. So we say it's shifting to the left. It's going to keep proceeding in that backwards direction till it finds a new equilibrium, and then the forward and backwards rate will be the same again. This is something that's pretty tough for people, and I think it takes a little bit of practice. I have a graphic that I think is helpful. We will not be able to get back to where we started. You are not going to the original equilibrium point. You are not going to be at the original ratio that you had. You can't completely undo whatever got messed up, but you can get better off than you were. Okay, you can't get back to where you started, but you can at least get better than when it was completely messed up. So we will have a new ratio that we're looking for. A lot of these problems are going to ask you, when I make this change, what will happen to the concentration of chemical A? Will it go up or down or no change at all? What will happen to the concentration of chemical B? Will it go up or down or no change at all? So a lot of times we're looking for these increase or decrease type answers. Sometimes though, your answer might be that you have a slight increase or a slight decrease. Because you can't get all the way back to where you started, sometimes you may just be a little bit worse than where you were when you started, and we'll use the phrase slight to indicate that. So here's the graphic, okay? Let's say that at this point, this is before we do a reaction, before we do a stress. The reaction is at a nice equilibrium position, forward and backward rate are equal, everything's wonderful. And then I come along and I dump in a whole bunch more nitrogen. So when I have stressed the reaction out, it's not at equilibrium anymore. I now have way more nitrogen than I started. So the reaction will proceed in whatever direction is necessary to use some of it up. So it's going to come back down, but it can't get all the way back down where it started. It can't get all the way there, okay? So it's going to come down lower than the worst part, but do you see how we're just a little bit higher than where we started? So compared to where we started, we have a slight increase. It was good. I really screwed it up. I made it way too much nitrogen. The reaction tried to use some of that up. It got to a new place where, okay, we're not all the way where we began, better than we were, okay? So it's really important that whatever your stressor is, whichever thing you've done to stress out your reaction, you got to understand that you're not going to make it all the way back to your beginning point. Some people have good luck with actually sketching this on their paper in the beginning, and eventually you'll get pretty used to this. So let's talk about changing pressure for a minute. Increasing the pressure causes the molecules to get crammed tighter together, right? They're now closer together. And so if you can reduce the number of moles of gas, you will relieve some of that pressure and you'll give them a little bit more space. So if you increase the pressure, in order to lower how crowded they feel, you gotta proceed in whichever direction will result in fewer moles of gas, okay? So if the right side of the equation has less gas moles, move that direction, make more of those. You're combining things together so that they're not as crowded in the container. If the left side of the reaction has fewer moles of gas, well then the backwards direction is the way we'll go to combine things together to relieve some of that crowding that we're feeling. And then the opposite is true. If you reduce the pressure, now they're too far apart. I like to joke that they feel lonely, right? And so they're going to go in whatever direction will get more gas particles to kind of fill up that empty space. You have to be careful not to count the moles of total chemicals. You're only counting the moles of gas. Remember, solids, liquids, and aqueous are not really affected by pressure changes. So you really are only looking at the gas particles if you're dealing with a pressure. So let's do an example of this. On the left side, I have 4 moles of a gas. On the right-hand side, I only have 2 moles of a gas. If I increase the pressure, all these chemicals are crammed too close together. So what has to happen is these ones are going to combine to proceed in the right-hand direction, the forward direction, so that we have fewer moles of gas particles and they don't feel so crowded. That's going to lower the pressure back. It won't go all the way back down where it started, but the pressure will be lower than it was when it was all messed up. If you decrease the pressure, well, now there's not enough moles of gas. So let's go in the backwards direction. Let's go to the left. Let's take some of these ammonias and break them apart. Now we have more particles floating around. It will fill up that container more, and it will get that pressure back up a little bit. It won't go all the way back where it started, but the pressure will at least be higher than it was at its lowest point. I think equilibrium is one of the hardest topics conceptually for students all year. It may not necessarily be the hardest chapter we do, but it is pretty hard for people to wrap their head around this idea. And I really do think that part of the reason for this is that they have shown that through brain scans and things that teenagers do not have the part of your brain developed fully that truly understands cause and effect relationships. And equilibrium is all about cause and effect. And what they have found is that students that seem to be good at cause and effect are really doing what's called parroting. You've basically been taught a set of rules and you're following the rules you've been taught subconsciously, right? You don't really realize that's what you're doing, but you've been, taught from your parents and teachers over time, right? That, if you do X, the consequence is Y. And, when you're given a chapter like this that expects that you can truly grasp cause and effect relationships, and your brain is not finished developing until you're in your, mid to late 20s, you kind of have an uphill battle, don't you? Part of me wishes I didn't have to teach this, right? I feel like it's kind of tough trying to teach something to people when you know their brain can't quite grasp what we're trying to teach you. And so you have to understand that what you got to be able to do is get to the point where you can parrot it back to me. I'm teaching you a set of rules, and you are trying to show me that you can implement the rules that I've taught you for the cause and the effect. And one of the things I think can be helpful is to watch some videos about this. I can't really make good graphics and animations in my PowerPoint, right? But we have videos where people can do animations and things and really try to get you to have a visual. And if we can get a visual in your brain of what's happening here, you have a better chance of grasping the cause and effect relationship. So I've put together a bunch of video links here that I think are super helpful. They really do a good job trying to get you to visualize cause and effect and visualize the difference between quantity and the speed forwards and backwards, right? So at some point, please take some time and go through these videos. In class, we often watch these together, but if you're watching this video, we may not be watching them together in class, right? So on your own, trust me, and go watch these videos. You can click on the links inside the PowerPoint, which is linked on the class website. Okay. All right. The last thing is there is a worksheet that you can glue in your notebook that has 8 practice problems that walks us through the different types of stresses and practices shifting left and right. And then we'll practice trying to decide, will the chemical concentrations go up or will they go down? And so we're going to do these. I am going to put this in a separate YouTube video. So I'll link the YouTube video in this PowerPoint on the class website so you can walk yourself through these practice problems as part of the notes. All right, everybody, that's it for this part of the video, and then you can go find the other YouTube video to do these practice problems. Bye.